All right, good morning. Okay, so today will be the third lecture. We'll talk about games and adversarial search. So what will be different from last week is that now we'll consider settings in which we have not just one agent, but several other agents together with the agents that we want to control. And then we'll try to see how we can come up with a strategy to still reach optimal decisions, even though we have no control now over what the other agents could do. Okay? And so we'll do that in the setting of games. Not that games or video games are interesting per se, but because they offer like the mathematical framework, which we call a game, to study this problem. Okay? But what we'll see today can be applied every time you have or you want to have a computer program or something that has to take decisions within an environment in which there are other agents operating. Okay? So to start and motivate the algorithm that we'll see, I want to show you a few minutes of a video which is taken from a movie about it's called A Beautiful Mind. It's a movie about the life of John Nash, who was a mathematician, and he discovered many things. And he's, among other things, he's the godfather of what is now known as game theory, which is the framework we'll study a bit today. Okay? Do you know about this movie? Just a few of you. Okay.
Papers for 5 sessions. Not by you, gentlemen, beer. No, we're not here for beer, my friend. That arm fish moving in slow motion. Does she want a large wedding, you think? She say swords, gentlemen. Pistols at dawn. Have you remembered nothing? Recall the lessons of Adam Smith, father of modern economics. In competition, individual ambition serves the common good. Exactly. Every man for himself, gentlemen. Yeah, those who strike out are some of their friends. I'm not going to strike out. You can lead a blonde along, but you can't make a drink. I don't think he's up to that. Nobody move. She's looking over. She's looking at Nash. All right, he may have the upper hand now, but wait until he opens his mouth. Let's go. History book. Smith needs revision. What are you talking about? If we all go for the blonde. We block each other. Not a single one of us is going to get her. So then we go for our friends. But they will all give us the cold shoulder because nobody likes to be second choice. But what if no one goes for the blonde? We don't get in each other's way, and we don't some of the other girls. That's the only way we win. That's the only way we all get laid. Adam Smith said, the best result comes from everyone in the group doing what's best for himself, right? That's what he said. That's right. Incomplete. Okay. Because the best result will come from everyone in the group doing what's best for himself and the group. This is some way for you to get the blonde on your own. You can go to hell. Governing dynamics, Joe. Governing dynamics. Adam Smith. Who's wrong? Yeah. Careful. Thank you.
Okay, comments? So basically, the main idea that we'll talk about today is when you want to take decisions, you should not only consider your own goal, but you should also consider what the other agents will do. And it's only if you consider what they will also be doing that you will manage to get good and eventually optimal decisions. Okay? All right. So what will we see today? We'll see how to act in a rational fashion in a multi-agent environment, which means that we'll have, and we'll see how to do that, we'll have to anticipate and respond to the behavior or the actions of the other agents. And what is different, and really different and fundamentally different from before, is that we don't have control on the other agents. You don't know what they will do. You may guess what they will do, and you may make assumptions, okay? But they may decide to be optimal, or they may decide to be suboptimal. They may even decide to act randomly if they want. You don't know, okay? How can we, in this setting, then, ourselves take optimal decisions? We'll see an algorithm or a family of algorithms to do that, which is called adversarial search. So again, we'll frame this problem of trying to determine the best action as a search problem, similarly to what we have seen last week. And we'll see the main algorithm that we'll see today is called minimax, which is a way to directly obtain an optimal decision in this setting. And you will see that it's very short, like in 4 or 5 lines of algorithm, we can recover optimal decisions. However, this algorithm is quite inefficient, so we'll see how to make it a bit more efficient using alpha-beta pruning. But we'll see that this is still not enough. So again, we'll have to make assumptions. We'll not be able to, for most interesting problem, to compute exact solutions. So we'll have to resort to approximations. So we'll introduce heuristics, and we'll see a variation which is called H-minimax for heuristic minimax. And then we'll start making the problem a bit more complicated. And for the first time, we'll also see how to take decisions in an environment which is stochastic, okay? In which the outcome of the actions is not known beforehand. Okay? It's random. And then finally, we'll see a last algorithm, Monte Carlo tree search, which is like the main algorithm which is used today in 2024 when it comes to take decisions. All right. Okay, so let's get started. I have first to introduce a few definitions to introduce the concept of games. And once we have defined that, we'll be able to define a solution and hopefully an algorithm that retrieves a solution. Okay, so the first thing we'll define is a game. So a game will be simply an environment in which we have multiple agents, like 2, 3, or 10, or even millions of them if you want. And what is interesting in this scenario is that these agents, they may have either conflicting goals, conflicting interests, or they may also have common interest. Okay? For example, if you take the game of chess, we have 2 agents, and they have conflicting interests, because they all want to win the game, but they cannot win both at the same time. If you play, I don't know, like Bullet, you have 4 players in teams, so 2 of them have common interest, 2 of them also have other common interest, but you have 2 teams with adversarial interest. Okay, so as I said already, the opponents or the other agents may act arbitrarily, not randomly, or maybe also randomly, but arbitrarily. You don't know exactly how and how they will act. And that may happen even if we assume a deterministic, fully observable environment. Okay? Like, again, if you take the game of chess, the environment itself is deterministic. When you move a piece, you know exactly what will be the outcome. However, you don't know what your opponent will do. Okay, so that means the solution to a game now will be a strategy or a policy which specifies a move for every possible opponent reply. Okay? Contrary to the search problem in which we said that the solution was a sequence of actions that we could just execute blindly, now we have to anticipate for all possible scenarios because we don't know what the other player or the other agents will do. Okay? So we'll have to recompute basically in this case our decisions, our next action to take at every step of the game. Okay? And usually also we'll assume that the time is limited, so we have a fixed and limited computational budget, that we cannot go beyond. There are, again, multiple types of games, just as we had multiple types of environments or search problems. We may have games that are deterministic, in which the environment is deterministic, or stochastic. We'll see both of them today. You may have games for which we have perfect or imperfect information. Perfect means that you know fully the state of the environment, but also maybe also the state of the other agents. In a perfect, so that's the scenario we'll consider today. But we may also have games in which you have only imperfect information. You don't get to know exactly the state of the system, of the environment, nor do you know about the state of the other agents. Okay? And these scenarios in which we have only imperfect information is what we'll start seeing and covering in the probabilistic track of the course. Okay? So starting from next week. We may have 2 or more players. So today we'll make things easy. We'll assume that we have a deterministic game with perfect information and only 2 players. Okay? And we'll just see a slight variation in which the game is stochastic, but you see that it's quite easy to end. All right. So formally, a game will be some kind of search problem with the following components. First, we'll define, as before, a set of states. Okay? And for each state, you have to define basically the information that you store inside the state. Okay, so it could be like a tuple of variables, each of which describing a part of the environment. So first, we have a set of state, S. Then you have to define what is the initial state when you start the game. So S0 among the possible states. So for example, in the game of chess, we always start in the same initial state where all the pieces are put on one and the other side of the board. Okay, in some very specific, at some very specific positions. Then we have to define, given a state S, who is the current player, okay? Who is the player to move next? Who is the player to take the next action? And that's something that you should be able to derive from what you've put inside the state representation, okay? Because it's a function of a state. Then, as before, we need to define what are the possible actions in a state S. Okay, which is a mapping from a set of actions, from the set of states to the set of actions, or to a subset of it. Then we have a transition model. So here we assume a deterministic environment. So the transition model is just a function mapping a state and an action to the next state S prime. Result, which is now a mapping between a pair of state and action to a state. Okay, and then we also need a terminal test. Which says whether or not the game is over in state S. Okay, so it's just a Boolean function which returns if the game should continue or not. Okay, what is different from before is that we also need a utility function which is mapping a set, a state and a player P to a scalar, to a numerical value for a game that would end in a state S. Okay? So if you have a state S for which terminal is true, you have a terminal state. Okay? Then you can evaluate the utility of that state, which would give you some numerical value. So for example, again, in a game of chess, if the game is over, then you have three possibilities. Either the player has won, so the utility is +1, or he has lost, the utility is 0, or it's a draw, and the utility is 0.5. Okay? So this, of course, these values, they are dependent on the game that you are modeling. Okay, so once we have these elements defined, then we can define the concept of a game tree, which is similar to the search tree that we had before. So a game tree will be what is induced by the initial state, the state from which we start the game, the actions S that we can take at any state S, and the transition model specified by the result function. Okay? And so this together define the game tree, which define so where any branch in the tree corresponds to a possible game, a possible episode of the game. Okay? It's one way to have played the game. So of course, this game tree is huge, usually. So huge that, as before, we will not be able to just instantiate this tree inside a computer. But this is the game tree that we'll need to explore when we need to decide on the next action. Okay. Today, we'll also assume that we have a so-called zero-sum game. What does that mean? We say that a game is zero-sum when the total payoff to all players is constant for all games. So, meaning that when you sum the utility values there over all the players, you get some sum of utilities, which is some constant. And if this value is the same for all S, then you have a zero-sum game. Okay? So again, in the game of chess, you may have the first player who lose, getting a utility of 0, but the other wins, so it gets a utility of +1. So the sum is 0 + 1, 1. Or it could be the opposite scenario where the first player wins. In this case, we'd have a first utility of +1, but a second utility for the second player of +0. But the sum is still 1. Or it could be a draw, in which case both players get a utility of 0.5. The sum is 1 as well. Okay? And so in what we'll consider today will be two-player games. We'll consider two-player games that are zero-sum. And basically, in that case, what will happen is that the agents will share the same utility function, but usually flipped by a minus sign. Okay? Or another way to say that is that one will want to maximize the utility function, while the other will want to minimize it. Okay? So for example, we could define the utility as the score of the white player in chess. So of course, the white player will want to maximize the utility, but from the perspective of the other player, the black player, he will not want to maximize the utility of the white player. He will want, of course, to win, which will happen if it manages to minimize the utility of the white player. Okay? And when that happens, what will emerge is a strict competition between the agents in which if one of the agents wins, the other will lose and vice versa. Okay? That will not lead to a cooperation between agents. Okay, so let's take an example. So let's consider the game of tic-tac-toe, in which at every step we have to either mark a cross or a circle, and the goal is to draw an alignment of either 3 circles or 3 crosses. Okay? So the first player can only draw crosses, the second player can only draw circles, and one of them wins if there is an alignment of 3 circles or 3 crosses. Okay, so let's play the game. What would you play next? We have to start with the cross. Center. Who said that? You? Okay, the one next to you, what would you play? You, what would you play? Top right. Next, below you. Sorry, behind you. Middle left. Middle. This one? Okay. There, what would you play?
Middle right.
Middle right. This one? I don't know. You, in red?
In bottom right.
Bottom right. And across?
Bottom right.
Bottom right, sorry. Okay, behind you.
Middle right.
Okay, there on the front.
Middle left. No, top left.
Okay, at the very back. You? Oh, yeah, or you with the. It's over? Ah, yeah, sorry. Okay, so there is an alignment, you win. Okay, so it seems easy. How do you program that in a computer? Yeah.
Check for each tile which has the maximal possibilities to make 3 paths and classify them by that. And then if 2 are equal, take the one that blocks the most the opponent.
So come again, what's the strategy?
Assign to each tile
Yeah.
the number of alignments that you could make using it.
Okay, but how do you know that?
Well, the middle one, you're going to make 4 of them, which is the most. So you got to start with it.
Okay,
And then the corners make 3,
okay,
and the middles make 2.
okay.
So start by the middles, then corners, and then if there's an option, choose the middle.
Okay. If you do that strictly, you will lose. Because you never account for the actions of your opponent.
I said it before, but and if there is one alignment or one tile that blocks the opponent, and also, well, choose the one that gives you still the most while blocking the opponent.
Okay, so if there is an alignment which is almost complete, then you block it. That's what you do?
Yeah.
Okay. So this is a simple game. But what if we extend that and we win when there is alignment of 5 or 10 crosses? And we consider a much bigger grid. Would you wait until there is an alignment of 9 crosses until you block it? How do you do that? What do you code?
Well, I think, as I said, it scales. If you assign a value to each tile by how many alignments you can make and how many options it blocks for your opponent, then you get an optimal.
Okay. Anyone else? Yeah.
If we consider a bigger game, I think just a guess, we should consider if we are on the offense side or defense side.
Uh-huh.
Like we will need to evaluate the position of the enemy and detect who is the first one who is on the verge of winning or going to die.
How do you know that you are about to win?
Well, first easy way to do it is see how many signs are aligned together. That's
Okay, so you have a strategy which is game dependent.
state dependent, yes. Oh, yeah.
You could not use the same algorithm to win chess, for example.
Yeah,
Could you?
Yeah, it would be game dependent. The one I said.
Yeah. Okay, so we'll see an algorithm which we can apply to any game. Okay. It may not be efficient because we don't exploit necessarily rules about the game, but it will still be optimal. Okay? So to go there, we'll make a few assumptions. We'll assume a game which is deterministic, which is turn-taking, in which you have only 2 players, and which is zero-sum, okay? And with perfect informations, okay? So we are making our life very easy with all these assumptions. When I say turn-taking, it means that, of course, one player is playing after the other and vice versa. But you may have also scenarios where you can play at any time or continuously. Okay, we'll not consider this kind of games. But even with all these assumptions, there are many games that fall into this category, like tic-tac-toe, like the one we've played together, the game of chess, checkers, the game of Go, and many, many other board games. We'll assume that we have 2 players, and we'll call them max and min. Okay, one will want to maximize the utility, the other will want to minimize it. Okay, and we'll assume that in the initial state, the turn is given to the max player. Okay. Now, as I said already, if we just say that, oh, but this is just a regular search problem, then we would determine a sequence of actions, and then we just play this sequence of actions. But this would fail miserably because we'll never take into account the arbitrary moves of the other player. Okay? Like when we were playing, at some point, we decided to block some alignment, but this is the result of the actions of the others. Okay? So we need to adapt, right? So the search algorithm that we have seen last week will not work. So what we need to obtain is not a sequence of moves, but a strategy, a function, which specifies the move that we have to take in the initial state, but also the move that we would need to take after every possible response from the other player, and also after every possible response to every possible response, and so on and so forth. Okay? So that means if you project yourself, if you want to decide what is the best optimal action you should take, maybe a strategy would be to think, okay, what if you play some move, what could be all possible responses to this move by the other player? Okay, so that you can simulate because you know a transition model. So you can consider, okay, you move the first piece to some position, and then you consider what will be all possible moves in this new state by the opponent. Each of them will result in a second state. And then you can iterate like this recursively. You can say, okay, but what if then in these successors, I'm playing that or this other action? What could be the other possible moves? And so on and so forth, until you reach a state in which the game is over. So you've either won the game or lost the game. Okay? And so if you do that, if you project yourself in all possible parts of the subtree that you are currently in, then you can take an optimal action. Okay? Because you can use this knowledge to inform the decision you should take. So let's say we are at some state in the game tree. The max player has to take an action. Okay? And you have to basically pick one of them. But let's assume for now that, okay, if you are in S, you take action 1, 2, or 3. Okay? And because you have a transition model, you can simulate what would be the next state. Okay? And let's assume, that's a big assumption, but let's assume that you know for each of these successors the maximum utility that you can reach or that the max player can reach. Let's say that the maximum utility in S1 would be +7, the maximum utility in S2 for the max player would be +3, and the maximum utility starting from S3 for the max player would be, I don't know, -2. which action would you take? If I'm giving you these maximum utility values that you can reach, that the max player can reach. And here the max player has to take an action. Would you go for the first action, where you get a utility eventually of +7, or you go for the second action, in which you get eventually a utility of +3, or for the third action, in which you get a utility of -2? Who goes for the first? Raise your hand. Okay. Who goes for the second? Who goes for the third? Okay. Okay. Of course, you would go for the first action because you want to maximize your utility. Okay. The max player maximizes the utility. So you would pick this first action. Now the question is, but how do I obtain these values? It seems so easy. If I know, of course, these values, then it's trivial. Okay? Well, the thing is that you can apply this recursively. Now, in this next state, the next player to play is the mean. Okay? So that means you have the same problem. You have different possible actions to take for the mean player. Let's say you know these values, -3 plus. So in this state, you know that it's your opponent who has to play, okay? And your opponent is trying to minimize your own utility. So what would be the action that it should take? If it's rational, if your opponent is rational, should it take the first action? Should it take the second? Should it take the third? No, it will take the second. Okay, so you can do so until you reach a state through some action, which is a term. I will do it with a square. Until you reach a state which is a terminal state. If you are in a terminal state, you know that, well, there is no more action to take because it's terminal. The game is over. But in a terminal state, you can evaluate the actual utility using this function. So you know the value by just evaluating the utility. Let's say it could be +7 for the max player. Okay? And in this case, you don't have to do anything anymore. So that means if you do this trick, if you follow this procedure, you can just, at every step, ask for, assuming that you know the maximum payoff for one or the other player, then you can take the decision at every step which you maximize or minimize depending on the player until you reach a terminal state. For the terminal state, you know you can evaluate the utility. And so that means when you explore the tree up to the end, then in the recursion that we'll implement, it's only when we reach a terminal state that we'll be able to backtrack the values up into the tree. Okay. So if we implement that, it's 3 lines. So we'll define the minimax value of a state S as the largest achievable payoff, the largest utility for the max player from state S, assuming that its opponent, the mean player, is optimal. Okay? And how do we do that? Well, we'll say that the minimax value of some state S, well, it's either directly the utility of the state if the state is a terminal state. Okay, so it's the utility S for the max player if this is true. So if S is a terminal state, so if we are in this scenario. If we are if S is not terminal, then we'll say that the maximum, the largest achievable payoff for the max player, if the current player is the max player, is the largest minimax value among the successors of the state S. Okay? So the minimax value for state 0, when max is the current player, is the largest minimax value of the successors of the state S. Okay? So in this case, the minimax value of S0 would be plus 7. That's the value, that's the max value among these three, this one. Okay? And on the other hand, if the current player is the mean player, then from the perspective of the max player, the minimax value is the lowest minimax value of the successors of the state S. Okay? So the minimax value of S1, for which the current player is mean, is the lowest minimax value of its successors. The successors are these three nodes. The one with the lowest minimax value is this one with a value of plus 7. Therefore, the minimax value of the parent of that node has a minimax value of plus 7. Okay? That's it. If you do that, if you manage to compute this minimax value, then if you are playing the max agent, then you just have to follow the action which leads to, to a successor for which the minimax value is the largest among the successor of the current state. Does that make sense to everyone? This is the algorithm that you will have to implement in the first project. Except it will not be about tic-tac-toe or the game of chess. It will be about Pac-Man, in which there will be ghosts, and you will have to account for them. Okay. Okay. Okay, so as I said, the optimal next move is to take the action that maximizes the minimax value in the resulting state. And so we are doing that because we make the assumption that the opponent is optimal, which is the same as saying that we maximize the worst case scenario. Okay, we assume the worst, and then we decide on the next action to do, assuming that the worst will happen. Of course, if you know that your opponent is not optimal, and you know why it's not optimal, then you can also exploit the weaknesses of your opponent. Okay? But we'll not make these assumptions today. Yes?
So for minimax, do we always consider that we're able to compute the whole tree down to terminal test all the time?
We'll see in a few slides that there is no way we'll be able often to reach the end of the game tree. And so we'll not be able to, or even if we could, there will only be a few branches that we can explore fully until we reach a terminal state. So, because if we want to, for example, compute the actual minimax value of that, you need to explore almost the entire tree, which is too large. Like just take the game of chess. Or maybe just this one, simpler. Like when we start, how many actions can we take? 9? Then for each of these 9 actions will result in a next state. Let's say we are there. How many actions can we take from this state? 8. How many actions can you take from this state? 7. and so on and so forth. Okay? So in this case, we would have a factorial number of possible games, sequences of states, 9 times 8 times 7 times 6, until we reach either a terminal node or until the board is completely filled. Okay? And this is for a simple tic-tac-toe game, in which we have only 9 positions. For Pac-Mans, you will already have tens or in the hundreds of positions for the ghost, for Pac-Man, for the score, and so on and so forth. Questions so far? Nope? Okay. So here you have another example where this is explained, in which the triangles pointing upwards correspond to max players, and the one pointing downwards correspond to the mean players. And then it shows you the minimax values which are computed. So you start the recursion initially nothing until you reach the end case of the recursion, this one. And so you will reach the nodes that you see at the bottom of the tree. They are all terminal, so you can compute the utility for each of them. Let's say 3, 12, 8, 2, 4, 6, 14, 5, and 2. And then the recursion backtrack to the parents. So for example, for this node, which is a mean node, then the minimax value for that node is the lowest minimax value of the predecessors, for which we know now the minimax values, because they were all computed before during the recursion. So in this case, the minimax value for B is the lowest among 3, 12, and 8, so it's 3. Okay, and now this value is known. Similarly, for C, the lowest will be 2, and for D, the lowest will be 2. And now that we have computed these 3 minimax values, then again, the algorithm can backtrack one level up in the tree, and the minimax value for A now will be the largest among the minimax values of the successors. So the largest among 3, 2, and 2, and in this case, the value would be 3. Okay? And then what action should you take next? If you are in state A and you are the max player, well, you should take the actions for which the minimax value is the largest in the successor. So in this case, it's the largest in B. Therefore, you should take the action, the first action. Okay? Okay, what about the properties of this algorithm? First, what about its completeness? So does it terminate? Yes, it will terminate, at least provided that the tree is finite. If you have cycles, like in the game of chess or in Pac-Man, which you will face, then the algorithm will not complete. Yes?
But in the game of chess, there are repetitions.
Yes?
But it's a draw.
Yeah, but I mean, if you are just playing randomly, you can just circle around and the game will never end. You can do that. Nothing prevents you from.
15 full moon draws.
Yes, that I don't know about, but
It's not mandatory anyway. Like, two players can decide to keep on playing even if there's 3 for repetition or 3 for removal, unless another proceeds it.
okay, whatever. I mean, yeah, it's not really important here. Optimality, is it optimal? It is optimal provided that the opponent is itself optimal. Okay? And actually, if you assume optimality of your opponent, but your opponent is not optimal, then the max player usually will do even better. And what if you make the assumption that your opponent is not optimal and it's predictable? You know how it will move. Okay, then you can exploit these weaknesses to obtain an even better strategy. Okay? But as soon as these assumptions are wrong, if you assume it's suboptimal and you assume that you can predict how it will play, but actually your opponent is optimal, then, okay, you are in danger. Okay, you will not be optimal anymore. How efficient is this algorithm? Well, basically, it's as efficient or as inefficient as DFS, depth first search. It really depends on how you implement the recursion. But so typically, the time complexity will be the same as DFS because you just explore during the recursion a branch of the game tree, and as soon as we have reached the end of the branch, then we backtrack. So the only thing that we need to store are the information along a branch. So that means we have to store M times B possible order actions in each of the M nodes in the branch. And the space complexity, in this case, is proportional to the size simply of a branch, M. Okay? Now the question I will ask you, do we need to explore the entire tree to obtain the correct and optimal decision? Who said no? Yeah, why?
Assuming that I want to be optimal, at each step I need to take only always the optimal action. So I don't need to explore the whole tree.
Yeah, but how do you know the optimal action without exploring the whole tree? If you look at just this definition, at every state S, we need to have explored all the successors. Okay, and for each of them, we'll do a recursive call to the minimax function. And so each of them will also call all the successors, and so on and so forth until we reach the end of the tree for the terminal states. So if you would just, if you just implement this, you will explore the entire tree.
I was thinking that as each step I will discard the non-optimal actions.
But how do you know they are not optimal if you have not explored everything yet?
But if we will explore the whole tree, it will take which complexity and which branch.
Yeah, that's another issue. Assume that we have the largest computer ever. Yeah.
From this definition, we have to know all the final states.
Yeah.
In case we have to explore everything.
Yeah, if you run this, you will explore everything. The question I'm now asking, do we need to do that to obtain the correct decision?
Yes.
No. Yes.
I guess you're inferring that we should put a new function that would kind of evaluate the situation.
Not yet.
Not yet.
Yeah, you.
If we keep the best thing that we can obtain, the best evaluation, and we find best response for the opponent, we can stop looking.
Okay, so let's take an example. So the same example as this one. Okay, so we have A. And what were the value? 3, 12, 8, 2, 4, 6, 14, 5, 2. Okay? So let's assume that we start the minimax algorithm on this node. Okay, we have 3 actions leading to these 3 successors. They are not terminal. For each of them, we have 3 other actions. And let's say we are currently at this state in the recursion. So we call the minimax on the three successors. Each of them are terminal. Okay? So in this case, we will have directly the utility for the first successor 3, the second successor 12, and the third successor 8. Okay? And after that, the recursion will backtrack and will say that the minimax value for B is the lowest among the minimax of the successors. Okay? So it's 3. Right? Let's assume now that we are in this state. And we are exploring we are computing the minimax value of the successors. Okay? The minimax value of the first successor will be 2 because it's a terminal state. Okay? So that means the minimax value for C will be at most 2. Right? The minimax value for C will be so. If we have not yet computed these utilities, when the first recursive call to the first successor backtrack and with the value of 2, since C is a mean player, we know that, well, if C takes this first action, it will get eventually a utility of 2. Okay, and since C is minimizing its utility, that means the utility of C is at most 2, right? Okay, it's some value between minus infinity and 2. Okay? But if we look at that node, it's the max player having to move, and he has the choice between, he wants to maximize. So he knows already that if he goes for B, the payoff will be 3. And the payoff for C will be at most 2. So you know already that if B is optimal and always following the largest payoff, he will never go in this part of the tree, because there is already another action along the branch for which the largest payoff is largest than the payoff here for C. So this, we don't even need to do the course. Okay? Okay, so this is what you have there on the slide, where it shows similarly, but using a different explanation, that you can actually compute the correct minimax value for the root without having to explore or to know the utility for all the nodes in the tree. And so in this case, if I say that I don't know the values for these two, okay, but I can make the same reasoning. The minimax value for A will be the max among the minimax value for B, C, and D, which are themselves the mean between 3, 12, and 8, and the mean of 2, X, and Y, and the mean of 14, 5, and 2. Okay? So the mean for these three scalars is 3, the mean for these three scalars is 2. And now we have the max among 3, some value which is at most 2, and 2. So of course the max is 3, whatever the values of X and Y. Okay? So let's call this value Z, then where Z is bounded above by 2, then the max between 3Z and 2 is 3. Okay? And that shows you that, yes, we do not need to explore the entire tree to compute the exact and correct and optimal actions. Okay, there you have an example where I'm showing exactly what I did on the blackboard. I will not go over that again. Okay, let's finish this part, and then we'll do a break. So we can formalize this in an algorithm which is called alpha-beta pruning. And so just to take a step back with a more general scenario, let's assume that the minimax algorithm is currently stuck at this node n, okay, for which the player is the mean player. Okay? So the way we could compute the minimax value for this node n would be by just exploring iteratively, so one after the other, the successors, and for each of them we would compute recursively the minimax value. Okay? So we are currently in this loop over the first, second, third, and so on child nodes or successors of n. And let's say that we maintain the current best estimate of the minimax value at n. Okay? So if we want to minimize it, so we'll get a first scalar, let's say 10. And so we'll say, after having explored the first child, that the current estimate for the minimax is 10. Then we explore the second. We discover that the minimax value for the successor is, let's say, 7. Then in this case, we update the current estimate because this estimate is lower than 10. Okay, so it becomes 7. So let's call this value v. And if we notice that v, the current estimate for the minimax value at n, becomes lower than the best value for the other player, and let's call this value a along any other actions connected to the going through the same branch, then we know that the max player will never reach n. Okay? So if alpha, let's say, is the best possible payoff along the branch connecting the root to n for the other opponent, for the max player, okay? Just as we had there, we were currently exploring C, and let's say the best action for the other player along the branch from the root A to C, in this case, the best action for the other player, as we have currently computed, is this one. Okay, so in this case, the value of alpha would be 3. And so if we notice that the current estimate v that we are computing for n becomes lower than alpha, then n will never be reached by an optimal max opponent. Okay, and therefore we can use this to stop the recursion and directly backtrack. Okay, the values that we backtrack basically are completely irrelevant in this case. We can do the same from the other player perspective. So if we define beta as the best value, in this case the lowest, at any choice point along the path or the branch for min, then in this case we can halt the expansion of a max node instead of a min node as soon as v, the current value for the node that we are computing, as soon as it becomes larger than beta. Okay? And when you put these two strategies together, then we can rewrite minimax using this now a bit longer algorithm, which we call alpha-beta search. And so it's made of 3 functions. A first function in which we call, because we assume that we start from the max player, in which we call a function max value, which will compute the minimax value from the point of view of the max player in the state. And what we also pass as argument to these functions are the current values, alpha and beta, computed along the branch. Okay? And so let's take this one, because it's the same as the one we consider. If we are computing the mean value for some state A and the current value of alpha and beta are passed as argument to this mean value function, then what do? If the state is the terminal state, then we just return the utility of the state as in regular minimax. However, if it's not a terminal state, then we have to iterate over the successors. Okay? For each of them, we have to compute the minimax value, and we'll pick the one for which the value is the lowest, because that's a mean node. Okay? How do we do that? So we say that initially, when we have not visited any successor, the current estimate v is plus infinity, so right? Any value will be necessarily lower than that. And then for each action, or for each successor, so we do a recursive call, and we do a recursive call on the next state, as given by the transition model, in which we assume it's the max player to play. So we call now the max value instead of the mean value. We pass the current values of alpha and beta. That will give us some scalar value, which we compare to our current estimate, v, and if that value is, and then we say that the new value for v is the minimum between the current estimate v and the value returned by that function. Okay? And then we implement this trick, which is to say, okay, if we notice that v becomes lower than alpha, this value, this best value for the player along the branch that we are currently in, then we stop and we just return v. Okay? Also, what may happen is that the current node becomes the best branch for the mean player. In this case, we have to update the beta scalar, and we would do so by comparing the current value of beta to the value v that we are currently computing for the node n. Okay? And we implement exactly the same function, but by flipping the two players in the max value. Okay? And so if you do that, if you implement this, then you will have implemented a more efficient minimax algorithm. What are the properties of alpha-beta search? Well, the first one is that it remains complete and optimal. Okay? It preserves these good properties of minimax. Okay? We are not making an approximation. We still do an exact computation of the minimax value. However, hopefully, what we've reduced is the time complexity. Okay? Because we have pruned parts of the tree. But actually, the effectiveness will depend on the order in which the states are explored. Okay? And we can make assumptions. If the states could be explored in perfect order, then alpha-beta search would only explore b to the m over 2 nodes instead of b to the m. Okay, so it's as if we had cut or reduced the depth of the tree by a factor of 2, which is nice. Okay, but it's under the assumption that we are always picking the next move to explore. Okay? Or another way to say that is that alpha-beta search can solve a tree which would be twice as deep as minimax can solve in the same amount of time. Okay? Or another way also to say that is that it's as if you were reducing the effective branching factor, so the number of actions you have in the game, to square root of b instead of b. Okay? And the space complexity remains the same. Okay, let's take the game of chess, and let's reason for 2 seconds about the size of this tree. In the game of chess, we have approximately a branching factor of 35. So it depends, of course, on the current state of the game, but approximately, on average, you have up to 35 actions at every step. The depth of a typical game would be 100, so we make 100 moves until we reach a terminal state. Again, these are just average values, which means that b to the d is 35 times 100. Okay, so that's 10 to the 154 nodes in the terminal level. Okay, there is no way we'll be able to explore that. Okay, but now you know about alpha-beta search, and what I'm saying is that, okay, if we could somehow determine the best way to explore the nodes, it would reduce effectively the size of the tree by a factor of 2 in depth. So that means we would get b to d over 2, so 35 over to the 15 instead of 100, which would be 10 to the 77, which is still too large. Okay? So that means for most problems, finding the exact solution with minimax will usually be intractable, meaning that we have an algorithm, we know it's exact, but it's just taking too long to compute. Okay? All right, so let's take a break now, and we can resume at 9:50. 1, 2, 3. OK, c'est bon. Okay, we'll resume. Okay, so just to do a quick recap, we've been talking about games. Games are defined for when you want to take decisions in environment for which there are multiple agents, and we have formalized that in terms of this list of elements. We need a set of states. We need an initial state in the set of in the state space. We need a player function which tells us who is the current player. We need an action function which defines the possible actions in a given state S. We have a transition model, so we know what will be the result of taking some action A in some state S. We know how to determine that a state S is terminal or not. It's terminal when there is no more action to do. The game is over. And finally, we have also defined a utility function which says that if S is a terminal state, it gives you a scalar value which represents the payoff, the utility, the score for the player P. Okay? Now, given this, we have covered a first algorithm, minimax, which gives us a way to determine the next action to perform if we want to be optimal. And it's simple. It says that you should always follow the action which lead you to the largest utility, to the largest payoff. Okay? So you just compute the utility over the minimax value over the successors, and then you pick the action leading to the largest minimax values. Now, how do you know the minimax value for the successors? Well, you do. The only thing you have to do is to call recursively that minimax function for the successor states. Okay? Until you reach a terminal state in which there is no more action to be taken, and the utility or the minimax, or rather, in which the minimax value now is directly the same as the utility of that terminal state. Okay? We have seen that, okay, and we can just implement this naively. It will be complete and optimal, but we can make it slightly more efficient using alpha-beta pruning. But to be honest, for most concrete problems, even using alpha-beta pruning will not really help you because the game tree is just too big. And so we need something else. Yeah, just before that, before seeing a solution to this problem, there is also one thing that you should take into account, which is the fact that as for search problems, you may have states that are repeated. You may reach a state through two different branches, or through two distinct sequences of actions could lead to a same state. If you just consider this is a tree, this is a game tree, you will face the same issues as for the search problem. You will recompute things many times without realizing that you're recomputing things that you have already computed before. Okay? So you can go around that using a transposition table in which you will store basically the state that you've already visited. So similarly to the closed set in the graph version of the search algorithm that we have seen last week, it's a good idea to store the evaluation of a state such that future or other occurrences of the state do not have to be recomputed. Okay? And that's something certainly you will have to do also in the first project if you want your function to ever terminate. Okay, so what if we have a huge game tree, which usually will be the case, and our time budget is limited? You want to take an action within the minute. How do you spend this budget? Okay, if you just apply minimax and then stop, supposedly you will not have a very good action after 1 minute. So what we can do is to try to estimate parts of the tree that we should explore, but we don't have the time to explore. Okay? And so we can define an approximation of minimax, which we'll call heuristic minimax or H minimax. And the idea will be very simple. We'll replace the where is it? We'll replace this if statement, which corresponds to the terminal case of the recursion, and we'll design it such that we'll stop earlier than when we reach a terminal state. Okay? And we'll say that we have a cutoff function, a cutoff test, which will decide, and that's something you have to implement, and you are free to design that however you want. But it's a function which tells us, okay, I think I've explored long enough. In this case, I should stop the recursion and return some scalar value. Ideally, the value that you should return when you decide to stop the recursion should be as close as possible or exactly the minimax value that you want to compute in the first place. Of course, we'll not be able to evaluate this minimax value, because if we could, then we would not be doing that. So we'll have to make a guess about the value of the state. Okay? So we'll have also to implement another function, an evaluation function, which in this case will be heuristic, which makes a guess about the payoff, the utility in state S, or that we can reach in state S by playing optimally the max player. Okay? And other than that, the two other cases are the same. If we are still within the recursion and the current player is the max player, then you return the largest minimax value, but now it's not the exact minimax value. These are the estimated minimax value among the successors. Okay? And similarly, for the min player, we would return the lowest estimated minimax value. You also see that there is this d variable, which is a new argument in the function, which is a variable in this case which simply corresponds to the depth of the recursion. It would start at d equals 0. And then when we make a recursive call, like these two, we say that d becomes d plus 1. So we know the current depth of the recursion, and that's a piece of information that you can use when you evaluate the cutoff. For example, one simple cutoff would be to say, I stopped the recursion when I reach a depth of 10, and that's it. Okay? Yes, you had a question?
Yes, I'm not sure I understand how the depth works. Because let's say I want to calculate the H minimax for depth 20.
Yeah.
And on the next iteration, when I'm calling H minimax again recursively, I was thinking that I would call it with the 19th, like -1 instead of +1.
But yeah, this is just dependent on what's going on inside this. You could have in the cutoff test definition, you could have something if d is larger or equal to 20, then return true. Otherwise, return false.
It's more about the d plus 1 that I'm concerned.
Yeah, but so that would work exactly in that case. Because as long as that value that you pass is lower than 20, the value of the cutoff test would be false. Okay, so you would not be in this first case. And it's only when you go higher than the threshold you would have set in that function that you would stop. Okay, so you could just concretely say that You stop when d becomes larger or equal to 20. Okay? Okay, then will come the question, but okay, how do I design this evaluation and this cutoff functions? And yeah, this will be the main problem you will face, because this is how you get a good or a bad decision at the end. If you have a poor evaluation function, you will do poorly. If you have a very good evaluation function, which is as good as the minimax value, for example, then you would be optimal. But there is a whole continuum between these two cases. All right. So an evaluation function, eval, should return an estimate of the expected utility of the game from a given position. Of course, since we don't want to explore the tree, we should not put too much compute inside that evaluation function. And so one thing maybe you should not do is to run another algorithm inside the evaluation function. So ideally, this computation must be short. That's the point of doing H minimax. And that's very important, the evaluation should order the state in the same way as minimax. If you manage to order the states in the same order as the one you would have when you order the nodes by their minimax values, then you will make the same choices. And so you will be optimal. Okay? So if you manage to do that, just ordering the state in the correct way, then you can be optimal, even if you are never able to compute the actual minimax values. Okay? Right. And finally, in non-terminal state, the evaluation function should be strongly correlated, of course, with the actual chances of winning. And this is where you can put knowledge about the specific game that you want to play. It's inside this evaluation function. Okay? And so in the first ideas that you had about how to play the game of chess or how to play tic-tac-toe, okay, you can do so now by just using an evaluation function in which you put this knowledge. Yes?
I don't understand the last point. Like, what do we mean by correlated?
But it should be that, okay, when you reach a term, well, let's say you say, okay. Let's say you are there. You run H minimax, the cutoff is true. So now you have to make a guess, even though there are actually actions. It's not a terminal state. If the actual minimax value, for example, for this one was +7, the value that we computed before, the guess that you make should be close to that or correlated to this with this value. If you make a guess and you say, I don't know, it's the mean, you say, I don't know, +100, it's quite far from the truth. But in this case, it's so far off that it will also lead to a different choice for the max player. Okay, because for the min player, it will minimize. So if you make a guess of +100, the min player then will think that it should follow this action. Okay. Okay. One interesting observation is that when you design a cutoff function, maybe you should try to do so. You should try to stop the search when you know that the value of the game will not flip or swing in a huge fashion from one step to the other. So for example, let's say you have these two scenarios. The boards are all exactly the same except from one position, the tower, which is there in the corner at the bottom right in this first board, and here the tower just to the position next to it. And let's assume that the current player is the white player. From just the representation of the states, these two states are very, very similar. All the pieces are at the same positions, except for one, which is just at the position next to it. However, in terms of the value or the payoff associated to each of them, they are quite different. Why? Yes?
Because the white can take the black queen.
Exactly. So in this position, the obvious next move is to use the tower to obtain the queen, and then you gain a huge advantage. Okay? So these are quite. So this is something that you should avoid. You should not stop the recursion in between these two settings. Otherwise, that may lead you to quite wrong decisions. Okay? And so what we say is that the cutoff function should only be applied to positions that are quiescent, meaning it's just a fancy word to say that nothing will happen in the near future from that state onward. Okay? Okay. Now, more interestingly, what will happen when you play with this algorithm? You will basically have the freedom to set when you stop the search, when you decide to cut off the recursion, and also you will be able to insert a good or a bad evaluation function. And then there is this so-called horizon effect, and which is the following. So it may happen. So we know that the evaluation functions are imperfect. Okay? It's an evaluation function. We know that they will not be the exact minimax value. What will happen is that if you don't look deep enough in the tree, then we may have bad moves that are actually bad, that may appear as good moves because you estimate them as good moves. Okay? And you don't recognize that they are bad moves because the consequences of going through these states are only revealed beyond the horizon, beyond the part of the tree after which you stop. Okay? And vice versa. You may have actual good moves that you estimate as bad moves because the consequences of these good moves are only revealed after or beyond the search horizon. And one simple rule that you can remember is that the deeper in the tree the evaluation function is buried, so the deeper you do the recursion, the less the quality of the quality of the evaluation function will matter. So, meaning, if you decide to stop after just 2 moves, you must be very, very confident about your evaluation function. That seems obvious. If you say that you have a poor evaluation function, which will be so-so, but you explore the tree up to a depth of 10 or 20, then usually you will be a better scenario in this case. Okay, let's take an example to show you that. With Pac-Man, 2 ghosts, 1 dot. The goal for Pac-Man is to eat this food. What should it do next?
Move south.
Sorry?
Move south.
Move south. Yeah, it should go down and eat the ghost. Okay? And this is actually what will happen if you use, so let's say we run Pac-Man using this heuristic minimax algorithm. We say that we stop the search after a depth of 2. So we don't visit much of the game tree. And we'll use as an evaluation function a function which will be such that the payoff will be larger the closer will be to the food dot. Okay, so the closer you are, the better. Okay. So you go south, then you continue running H minimax. But then what happens is that if you go south, Pac-Man is trapped between the 2 ghosts and never wins. The optimal action is to go up. It looks like a bad move, but if you go up, then that gives Pac-Man just a window of opportunity to not be trapped between the 2 ghosts. And in this case, to win the game. And that's something that you can do using the same poor evaluation function, the closer the dot, the better, but you just evaluate it at a depth of 10, so much deeper in the tree, rather than at a depth of 2. Okay, so you go up. That seems like a very bad thing to do. Sorry, these videos are taken from somewhere else. Up, and then you continue. And now when it goes, so basically the blue ghost has to make then a decision to either go right or left. And when you know that, then you can just go in the opposite direction and you win. Questions? Okay, so this was the case for two-player games. What if we have more than 2 players? What if we have n of them? Well, the algorithm that we have seen can be generalized very easily. So instead of having just 2 players with opposite utility functions, now what we'll say is that if we have n players, then at every terminal node, like the ones that you see there in green, we'll not have just one utility value, but we'll have a tuple of values where we have as many values as we have players. Let's say we have 3 players, red, blue, and green. So that means each node will be now labeled by 3 values. And the goal of an agent will be to maximize the value that corresponds to its color in the tuple. Okay? So the red player will want to maximize the first value in the tuple. The blue player will want to maximize the second value. And the green player will want to maximize the green value. Okay? And you can extend that to any number of agents. Okay? And we'll say that we have a zero-sum game in a multi-agent setting when the sum of these utilities are constant across all nodes. So in this case, it's not a zero-sum game. Okay, for the diagram there. So this is interesting because this now may lead also to cooperative behavior. It may happen that 2 agents discover that they should cooperate because this is what will lead eventually to their individual best outcome. Exactly as we had seen in the video at the very beginning. Okay, now let's move on. Yes? Yeah.
So they may collaborate, but they don't know why.
Yeah, they don't know why, but
I mean, if there's 3 agents, 2 of them end up with a score of 0.6 or a score of 3.3, what's probably going to happen is the 0.6 results. Because, I mean, they don't really cooperate. They're looking just for their individual.
But take into account the behavior of the others, which are themselves trying to maximize their own utility. Okay, so let's move on now to the next part about stochastic games. So what if now we have a game for which we don't know the outcome of the actions? So what I'm saying is that this thing we don't know it anymore. Or rather, we don't know it in this form. We don't have a function, a deterministic function, which tells us that, okay, if you're in state if you're in state S and then perform some action A, then necessarily you will arrive to some state S prime. The scenario that we'll now assume is that a state together with some action, A, may lead to several states. You could arrive to S1, but you could also arrive to S2, or maybe to S3. You don't know. Okay? So every time, for example, the game has some kind of random components, for example, I don't know, you have to throw a dice or you have to draw a card from a deck. You don't know the outcome. That's an action. So you cannot predict exactly what will be the next state. You can anticipate for all these next states, but you don't know exactly which one you will reach. Okay? So formally, now we'll go from a deterministic function, a deterministic transition model, to a probabilistic transition model, which will define as a distribution P over next states S prime, given some initial state S and some action A. Okay? So we'll assume that we know this transition model, but now in the form of a distribution. Okay? Okay, so as I said, in real life, yeah. Okay, now the question is, how do we take that into account? Can we modify the minimax algorithm that we have seen to cope with probabilistic transition models? Like, now what's different is that if you're in state S0, we were running this minimax algorithm in which we're just iterating over the successors, okay, over the actions, and each action was directly connected to one successor because we had a deterministic transition model. Now, what will be different is that if you are in state 0 and take the first action A1, we may end up in S1, but maybe also in S2 or in S3. So what do we do? Yeah.
I don't know if the word is like this in English, but ponderate the H minimax, I forget the name, the H minimax function according to the distribution, and decide.
What was the word you used? In French, if you want.
Pondérer les résultats de H, j'ai oublié le nom, mais je pense que c'était H minimax.
Yes.
Selon les distributions données.
Okay. Okay, so you say, okay, you know what will be the next state, and each of them comes with a probability value. And you will use these probability values to say it's more likely to go.
So if something, say, one of the action, one of the possible states has a good H minimax value, but this state has a low probability, but I have a big probability of another state S prime, which gives also a good. Then I might take the second one because I got confused in my state. Sorry.
Anyone can help? Yeah.
I have an idea, but I actually didn't listen too much to what you said, so I don't know if it's the same.
Okay, maybe rephrase that.
I
Yeah.
wanted to say, if you explore the tree
Yeah.
and you keep trace of all the final nodes,
Yeah. Yeah.
and you try to assess which ones are most probable,
Yeah.
you can assign a probability to each node that tells you there's a 10% chance that I get 10 score here, but here this path is.
But, okay, and how will you then use this information eventually to take a decision, to say I should go for this action or this other action? Yeah. Just even with regular minimax. Yeah.
We can multiply the probability of every state by its evaluation.
Yeah.
To try to balance the risk versus the reward.
Yeah. Okay. That's the correct strategy. So instead of saying we'll compute exact minimax values, these things actually don't exist anymore now. will compute the expected minimax value. Okay, and we'll do so by just considering all possible next states together with their own expected minimax values. And we'll say that the expected minimax value of this is the expected value of the expected minimax values of the successors, weighted by how probable it is to reach one or the other state. Okay, and that's given by the transition model. Okay, how do we do that concretely? Well, the first thing is how do we model this random component? One very simple way to extend the minimax algorithm to include that is to say that we have a third player. Okay? And that third player is some kind of chance node, which is just responsible for all the randomness in the environment. And this player gets to play in between every two, it gets to play after every move. So you have a human player, he decides to take some action, and then the chance node plays, decide on some random outcome, you reach a state, and so on and so forth. Then the next human player plays, but after that, you have the chance node playing this random component. So that means we would obtain now a stochastic game tree in which you see, as before, triangles pointing upward or downwards. These are for the max and the min player. But in between them, you have now the circles, which correspond to the random moves that may happen because of the probabilistic transition model that we now assume. Okay? And so if you are in state S, this one, and decide on some action, that will lead you to this circle, which is just a tuple, a pair of state and action. And from this pair of state and action, you have some possible successors, which are regular states. So from this pair state action, you can either reach this one, this one, this one, and this one, and this one. Okay? And now that we have this, we can rewrite the minimax algorithm as an expected minimum. Yes?
Should the chance player play between the bot turn, like before the next player? Because you're supposed to take a decision not to guess.
What do you mean?
I mean, the max here is our agent that is trying to reach
Yeah,
a decision.
yeah. So this is just to say, okay, you are the max player, and you decide you should move left. Okay? But before, I mean, you don't get, you cannot predict that you will arrive there. You cannot predict the next state, because in between your current state and the decision to take, it's as if this chance player was controlling you and will decide where you land. Okay? You see that the next state of the game is this one, but in between you have like these random outcomes, okay? And the possible results of these random outcomes are one of the possible successors as defined by your probabilistic transition model. Okay? So these circles, they are just like virtual states, if you want, which correspond to a pair state action, and then from this virtual state, you can reach one or the other successors, S prime, with a probability given by the probabilistic model. So for example, there, from this pair state action, you can reach this one with a probability of 1 over 36, this one with a probability of 1 over 18, and so on and so forth. Does that make sense?
I still don't understand why the chance would play before our player. I mean, I get why the other agents, because we don't know their actions, but our agents.
No, but what you say is wrong. It's not because the other agents. It's not because you don't know what they will do that they are random. What we are modeling here is the randomness of the environment. Like, for example, let's say I'm a robot, and my actions is to go towards you, or this direction, or to my left, or to my right. And I could have, as a transition model, if I'm currently in this state, I will reach with a probability of, let's say, 99%, and I decide to go left, I will reach this position. But maybe with 1% probability, I will fall, okay, and I will not reach this state, okay? So if I do that 100 times, maybe I will fall, okay? That's something that you can anticipate in this probabilistic transition model. Okay, so now that we have that, we can define expected minimax, which you will recognize as just a slight variation of the previous algorithm. So if S is the terminal state, we return the utility. If the current player is a max player, then we return the largest expected minimax as given by the result transition function. And this result, I mean, what I said is that I would define this in terms of probabilistic model. In the textbook, they don't exactly do that. They still assume a deterministic transition function, but in the result of that will project the state into a virtual state, and then from which there will be a random decision. Okay. So you assume that this result starts if the current player is max, you are in state A, and then you take the action A. This will lead you to a new virtual state, one of these circle nodes, okay, for which the current player is the chance node. So you, the recursive call now will lead you to this part of the function. And here what you do is that you return the expected value of the successors, okay? Where you say you can reach the first, the second, or the so on, or the next successors by going through some action R, which is random, but for which you assign some probability value, okay? And then you take the average, and that's the expected minimax value that you return, okay? All right. Now, as for minimax, the value of expected minimax can be approximated by stopping the recursion early, okay? Because you will, I mean, now the tree is even bigger because you have to consider all possible next states, not the only possible next states. So there is no way, again, you will be able to explore this tree fully, but you can do the same, define a cutoff function, and then an approximate evaluation function. However, what is different is that to obtain the correct move, as if you could compute the exact expected minimax value, the evaluation function should be now a positive linear transformation of the expected utility of the states. Okay? Contrary to before, where we only needed to be able to compute values for which the minimax ordering was preserved. Now, this was the guarantee to obtain the optimal decision. Now, if you want to remain optimal, you need an evaluation function, which is a linear transformation of the expected utility of the states. Okay? So, for example, if you take this scenario, okay, and you compute the expected utility, so let's say we are there. So in this case, these are terminal states. We take the largest. So the expected minimax for this node is 2. This one is 3. This one is 1. This one is 4. Okay. But to reach this state, we have to go through a chance node, okay, which will lead us with a probability only of 0.9, and it will lead us there with a probability of 0.1. Okay. So the expected minimax value of the chance node, in this case, is the expected value of 2 times 0.9 plus 3 times 0.1. That's 2.1. Okay? And similarly for the left part of the tree, where the expected minimax value for the chance node would be 1.3. And now the action that we would take, in this case, when you are in this max node, would be to take the action which is which leads to the largest expected payoff, 2.1. Okay? If you say that you can't estimate this thing, so you are using an evaluation function, let's say that your evaluation function is such that you estimate the value of 1 when it was actually 1, you estimate 20 when it was actually 20, you still estimate 30 when it was 3, and you estimate 400 when it was actually 4. These estimated values are in the correct minimax ordering. They are in the same order as this one. Right? However, when you compute the expected minimax values, you do the same. What will happen is that the action that will follow will no longer be the same. It will be to go right. Because now you estimate that the expected value, if you go and follow that second action, would be above 40, which is larger than the other value, which is 21. Okay? So this is just a counterexample to show you that it's not because you preserve the correct ordering of the expected minimax value that you would obtain optimal decisions. It's only if your approximation is a linear transformation of the actual expected minimax values. Questions? Okay. Okay. Now, for the rest of today's lecture, we'll go over another algorithm, which we call Monte Carlo tree search. It's a quite nice algorithm because it's very simple to define as well. You don't need any domain knowledge. You just need to be able to simulate a game or to play a game on a computer, preferably. And this leads to algorithms that are state-of-the-art when it comes to playing games. So, for example, examples like AlphaGo or other systems that are now much better than human players, they are all based on this algorithm. Okay, so how does it work? Well, one thing you may have noticed already is that if you were to pick minimax or rather expect heuristic minimax, for this to work well, you need a good evaluation function, right? What if you don't know this evaluation function? What do you do? This is the problem that MCTS, Monte Carlo tree search, tries to solve. And the main idea that or the first idea that it exploits is the concept of a random playout evaluation. So instead of saying, I make a guess there for the value of that node, according to some recipe that you have cooked up and implemented in your evaluation function, what you will say instead is that, okay, from there on, I will just make a guess, which is random, which is stochastic, and this guess, I will obtain it by just playing the game randomly from this position onward. Just assume that the two players now are just random players, okay? And you take random actions in between until you reach a terminal state. And whoever wins, okay, gives you an indication of how good it is to be in this state. Okay, so to evaluate a state, what we'll do is that we'll have the algorithm play against itself using random moves. And since everything is random, it's very cheap. We don't have to compute much. We just have to run the game, random moves, no compute is involved. We are not trying to explore at every step huge trees. We just take random actions. So it's very cheap, and we can repeat that thousands of times, okay? Even on a regular laptop. Now, a sequence of random moves from a state to a terminal state will be called a random playout. And if you repeat that many, many times, we'll use the proportion of wins as an evaluation of the state. Of course, if you play only once randomly, it's a very poor and noisy approximation. But if I tell you that, okay, actually I've run the game 1 billion times from there, and on average, the white was winning 75% of the time, that's a very good indication that this is certainly an interesting state. And what is interesting is that the strategy, well, does not require any domain knowledge. just need the game engine, which you have because we assume the knowledge of the transition model. Okay? Either probabilistic or deterministic. Okay? So just have to know the rules of the game, basically. And then you can simulate and evaluate this function. Okay, now that we have this concept of random playouts for the evaluation function, MCTS is also smart in its choice of the parts of the tree that it should explore next. Exactly as we had for the search algorithm with the fringe, which when we were using these priorities, we are basically saying, okay, this part of the tree, this node looks the most promising, therefore you should maybe start exploring this one first. We'll have something similar in MCTS. And so what it will do is that we will use these random playouts to incrementally determine what are the moves that are the most promising. Okay? And so what we'll do is that at each node n in the current search tree, we'll maintain two values. First is this function of just a table Q of two a table Q, which is a function of the node. So we have a table as tall as the number of nodes, and then we have a number of columns which correspond to the number of players. And so in this table, Q of NP will correspond to the number of wins of player P for all playouts that have passed through N. Random playouts in this case. We'll also maintain how many times we have visited a node N in this other table. Okay? Now the algorithm goes as follows. You would search the game tree by just repeating these 4 steps as much as you can. Okay? So it's very brute force, but this works very well. Step 1, you select. You have to select a node in the game tree to fully expand. So you start from the root. You select successive child nodes down to a node n that is not yet fully expanded. Then you expand. So that node n that you have selected, so if it's not a terminal state, then you just pick one of its successors, n prime. Okay? And then from this successor n prime, you play one random playout. You execute the game engine at random. That gives you either a win or a lose for the player, or something more complicated depending on the utilities that you're using. And then you backpropagate, so you use the result of the playout to update the information in the nodes from the root to the child n prime that you have created. Okay? So you backpropagate the information about who won the game along the branch from the root to n prime. You repeat that many, many times, thousands, millions of times. At the end, you get statistics about how promising are each next actions, and you use that to pick the next, the best next direct move. Okay, so to give you an example, let's say this is the current tree of MCTS that we have currently explored. Okay. So we are so let's assume there's 2 players, white and black players. Okay, it's for white to move, so the root node is for the white player. Okay, and you see numbers there. They correspond to the number of times. So you have, for example, 11 over 21. It means that we have executed 21 random playouts starting from this node, and among these 21 random playouts, 11 of them were leading to a win for the white player. Okay, then we have these ones where you see that the sum of the denominator should correspond to the denominator of the parent. Okay, and it says, for example, for this one, well, we have visited that node already 10 times, and among these 10 times, 7 of them were leading to a win for the black player. Okay. And you go the same for all the other nodes. Now, first, step 1, this is the current game tree, the current tree that we've explored. You select a node which is not currently fully expanded. Okay, so for example, we could select this branch and select this node where there is 3, 3. Okay, 3, 3 is not a terminal state, so we just add a successor to it. We expand it. Let's say that gives us this new state for which we have not yet run a random playout. So the denominator is 0, and we don't know yet the other value. Step 3, you simulate by just doing these random playouts. And let's say that after this random playout, we discover that the white player has lost the game. Okay? So then we use this new result to backtrack and update all the statistics along the branch connecting this child node to the root. So now this one, the parent, well, we have now run the game once, so the denominator is 1, and on this game, we have lost. So the numerator is 0. The parent of that node is a black node, okay, for which now we can increment the number of times we have played through that node. So now the denominator becomes 3 plus 1, 4. And that additional random playout led to a win for the black player. So we also increase the value of the numerator going from 3 to 4. And we repeat that up to the root. Okay? And you do so, you run this algorithm, these 4 steps, thousands of times, until you exhaust your budget. Let's say you are allowed for 1 minute of compute, and then that's it. And then what you will pick as the next move is the node for which you have made the most simulations. Okay, so in this case, the move you will pick is to go there, because this is the one for which the number of simulations is 11. It's larger than all the others. Why this is the case is because why we follow this action, the one for which we have simulated the most, because this is dependent on how we have selected the first that branch. And that's a key ingredient of MCTS. How do you select the branch? How do you select the node to expand? And here what we already face a very important concept in AI in general, which is the concept of exploration and exploitation. So given a limited budget of random playouts, the efficiency of MCTS will critically depend on the choice of the nodes that are selected in the first step. Okay? And ideally, what you should try to do is to explore nodes that you know already do look promising, but maybe you should not do that much, because maybe there are parts of the game trees which you have not visited yet that much, but that could be interesting until you explore them. Okay? So how do you exploit this current knowledge that you have? So that's the exploitation part with an exploration strategy. So there are many ways to do that. There are plenty of papers on this topic. One of these strategies, the so-called UCB1, upper confidence bound, which is a policy which picks the node n prime of some node n, which will maximize this expression. Okay? And so in this expression, you see 2 terms. This term, which is the ratio between how many times you have won the game for P over the number of times you have already visited that node n prime. If in the expression this term dominates the other, okay, then that means you will tend to keep exploring nodes that you have already explored many times, because this n is large, but for which you know that they are very good, okay, because the value of Q, number of wins, is large. Okay, so this is the term which is responsible for exploiting the higher reward nodes. And on the other hand, you have this exploration term, which will also force the algorithm to explore nodes that are less visited. Okay, and so the nodes that are less visited will be the ones for which you may have visited the parent a certain number of times, but not the child nodes. Okay, and so in this case, this term will get some numerical, will be some quantity which may be larger than this other quantity. And in that case, this term will, in this case, dominate and will force the exploration towards this part of the tree. Okay, so for example, if you have not visited yet n prime, okay, then this will be 0, and okay, this will blow up to infinity. Okay, there should be certainly an epsilon or something in the expression if you don't want this to blow up. But you see that nodes that you've never visited will have, may have quite an impact on this term. Questions on this? Yes?
Do you use this at every step or just at the first node? And
No, at every step, of course. Yeah. Well, actually, so let's say you have this tree. You compute this expression for all nodes that are not fully expanded, okay, for which we don't have yet all the successors. So in this case, that would be this one, this one, this one, this one, this one, this one, and this one, and maybe also this one if there is, let's say, a third action. You compute this value for each of these nodes, and then you pick the largest. You pick the node for which this value is the largest. And that gives you the node to expand. Okay. Last thing for today, which is quite important for most practical problems. So I want just to stress that in everything that we've been doing so far, we are making assumptions, and specifically we are making modeling assumptions. Okay? And the question you should always ask yourself, if you ever deploy some AI systems in the real world, is what if the assumptions that you make are not correct? And to show you that it's very important and that the consequences of assuming wrong assumptions can be quite huge, let's assume a very simple scenario or setup in which we have two agents, Pac-Man and a ghost. And then we'll make assumptions about the policies that are followed by these two agents. Okay, about their behavior. The first assumption, P1, is that we'll assume that Pac-Man, or we'll say that Pac-Man follows a depth 4 search, so h minimax up to depth 4, with an evaluation function that avoids trouble, so which will penalize Pac-Man if it goes too close to the ghost, okay? But also it should compensate with the fact that you want to get closer and closer to the food. And also when we run h minimax inside Pac-Man, we'll assume that the opponent, in this case the ghost, follows this other policy. Okay, this other policy for the ghost will say, P2, that the ghost also follows some kind of h minimax algorithm, but in this case limited to depth 2, with an evaluation function that will seek Pac-Man, so which will try to go greedily towards Pac-Man. Okay, so and basically the closer the ghost to Pac-Man, the better. Okay, and when we do that inside of the ghost agent, we'll assume that the Pac-Man, the opponent from the perspective of the ghost, will follow that first policy. Right? Then, we'll have so two other cases where Pac-Man still follows the same h minimax algorithm, depth 4, the same evaluation function, but we'll assume in this case that the opponent plays randomly. We'll not assume that the opponent follows this other greedy policy. We'll assume that it makes random move. Okay? All right. So, what do you think will happen if we run this scenario in which we have Pac-Man following the minimax policy, P1, and the ghost being adversarial, P2. Okay? What do you think will happen when I start the game? So in this case, we are in a scenario where the assumptions are correct. So Pac-Man will actually follow the policy assumed by the ghost, okay, and vice versa. The ghost will actually follow the policy assumed by Pacman. Okay? Does that make sense? It does not go towards the food because it knows and is correctly assuming that the ghost will go and tries to kill it. So it should move behind and go around the obstacle such that the ghost, because it knows that the ghost is also a bit stupid, it will just follow because it's limited by the depth 2 search. So it knows that it can exploit this. Then, because it can predict correctly that the ghost will just follow, and then it can reach the food. Yes?
So if the ghost uses a depth 4 search, same as Pacman, would that change?
Yeah, that will change the behavior. Okay. And if Pacman still assumes that the ghost follows the depth 2 algorithm, although the ghost follows a depth 4 or more algorithm, then Pacman will be in trouble in this case. Okay, let's assume now that Pacmans still follow the same policy and still assume that the ghost is greedy and should go and tries to kill it. Okay, so Pacman assumed that the ghost follows the P2 policy, but actually the ghost does not follow the P2 policy, just playing random moves. Yeah.
Pacman will wait for the ghost. It will wait around the ghost.
Yeah.
To be far enough from the point, and then it will go.
Yeah. Exactly. So Pacman expects the ghost to follow it. That's what it's waiting for the ghost, because it's only then that it can do the same trick of going around the walls. But actually, the ghost is just stupid and just making random moves. Okay, then eventually, by chance, the ghost reach a state in which Pacman can go around. Okay, Pacman still wins the game, but you see that its behavior is certainly suboptimal now, because if it had knew that the ghost was playing random moves, it would have certainly played differently. Okay, so let's see now what would happen when we assume that the ghost is playing random moves, okay? And in this case, Pacman would correctly assume that the ghost makes random moves, okay? And therefore would follow expecting minimax. What do you think would happen? Who thinks that Pacman will wait somewhere in this corner for the ghost to chase it?
One block away of the ghost,
Yeah.
and then run once he gets you, and then go and get to the food.
Yeah. Do you? Okay. So you say it will maintain some distance.
Yeah, one block, because we're going to stay.
Mm-hmm. Anyone else? Let's see. Okay. In this case, just going towards the food because it knows that under the assumption that the ghost is playing randomly, it's very unlikely to face the ghost when you just go straight to the food. Okay. What if Pacman still makes the same assumptions that the ghost is playing randomly, while actually the ghost is adversarial and tries to kill it? Yeah. Yeah. You?
It will try to go towards the food, then get too close to the ghost and get chased around, and then finally come back.
Yeah. Is that what you?
I see that Pacman is doing
Okay, we'll see. So it tries to go directly. That's the same assumptions, but since it's noticed that it's getting too close, then it tries to avoid it. So in this case, it's also lucky. It could have been killed by the ghost. Okay, so this is just to say that the assumption that you make and the fact that you call yourself optimal depends on the assumptions that you make. And if you have wrong assumptions, you may think that you're optimal, but actually you are not. Okay? So you'd better think twice about the assumptions that you're making when you implement such algorithms and deploy them eventually. And so that's why also assuming almost nothing about the adversary, like assuming optimality, like in regular minimax, okay, you assume the worst case, but and it's quite difficult then to solve, but when you do that, you know that you can be guaranteed that nothing bad should happen. Okay? But maybe you would be suboptimal because you could maybe have exploited the weaknesses of the other agents. Okay. Then there are a bunch of slides about state-of-the-art algorithms or programs to play games, checkers, chess, and Go. I will not go over these slides, but you can just check them if you're interested. This is just to say that these problems have been studied for decades now, and we are still making progress on them. One breakthrough happened almost 10 years ago with AlphaGo, where an algorithm using MCTS was used to beat the best human players at the game of Go, for which the branching factor is like huge, huge, huge. It's in the 300s or so. And so just the number of games that you can just that you have in this game it's a number that you cannot even understand. But still, it was beaten by an algorithm using MCTS. Using exactly the algorithm that we've seen, together with very good heuristics, which were, in this case, implemented by neural networks, which is something we'll see later on in the course. All right, so to summarize what we've seen today, we've talked about games, multiplayer games, and you can view them really as variations of search problems. The main difficulty and obstacle is to account for the fact that you cannot predict what will be the actions of your opponents. They may act arbitrarily. And so a solution is just to assume that they are themselves optimal. And a way to achieve that is by using the minimax algorithm, which is an optimal algorithm for deterministic turn-taking two-player zero-sum game with perfect information. However, it's usually intractable to evaluate, so we need to resort to approximations by cutting the recursion early using a cutoff test, and also by using a somewhat good approximation function. What you should remember is that the deeper you evaluate, usually the better, even if you have a poor evaluation function. Okay? And finally, optimal behavior, as I said, is relative and depends really and strongly on the assumptions that you are making about the environment or about the other opponents. Okay? So what we have seen today is exactly what you have to implement in the first project. The instructions are already online on the GitHub. The deadline will be in a month from now, so you can start. I will create the entry on Gradescope today, but you can already start. You have all the knowledge that you need actually now with what we've seen in this lecture to start the project. Just for your information, let me just switch. So we have released the grades, which are completely virtual for the first project, Project 0, which you did last time in class. You can check them online, but the median is really poor. It's 7 out of 20. The largest grade is 19. So don't be surprised. We'll use the same kind of evaluation for the actual first project, which will count for your final grade. Okay, and so maybe double check what you did wrong, ask us questions, such that you can generalize that to project 1. Yeah.
Is the number of submits accountable?
You can submit as many times as you want, and it's not taken into account to determine the grade. Okay? So usually this project 0 is like much better, but maybe it's because it was counting for nothing this time. But yeah, really take this feedback into account. If you do the same as you did for project 0, you will certainly fail project 1, which is harder than this one. Okay, so now we have the exercise session. We'll resume in 10 or 15 minutes, and we'll cover search problems.